Good morning, everyone. I am Radhika, working as an assistant professor in AML department at Annamacharya University. Today's topic on quantum computing. Why the world is shifting towards quantum computing. Quantum computing is just faster computers. It represents a fundamental shift in how information is processed. A new era of computation. As problem grows in complexity, classical mission struggles, and we'll see the difference between classical computing, supercomputing, and quantum computing. The information will be in the form of bits in classical computations and supercomputing, whereas in quantum computing, the information will be shared in the form of qubits, 0, 1, or in a combination of both, nothing but a superposition. Possibility states. In classical computing and supercomputing, the possibility states will be in discrete nature, whereas in quantum computing, the possibility states will be in a superposition. Calculations. Classical computing and supercomputing. The calculations will be in deterministic nature, whereas in quantum computing, it will be in a probability amplifier. Data processing. Boolean logics in a sequential. In classical computing and supercomputing, whereas in quantum computing, it uses the quantum logics in a parallel. Boolean logics may contain binary variables and logical operations. Boolean variables like 0, 1, true or false, yes or no. In logical operations like and, or, not. Whereas quantum logics is a framework that uses the mathematical structure of quantum mechanisms like superposition, entanglement, and inferences. Operations. Operations are in the classical and quantum computer will be Boolean algebra. And quantum computing, the operations will be in a linear algebraic over a Hilbert space. The processing style will be in sequential or limited parallel in quantum in classical computing, whereas in supercomputing's massive parallelism with thousands or millions of cores, and in quantum computing, the quantum parallelism using entanglement and inferences. Strengths. Everyday task, reliable, low and error rates. In the classical computers, large scale stimulations like physics, genomics, and high precision in supercomputers. And whereas in quantum computing, optimization, cryptography, molecular modeling, problem intendable for the classics for the quantum computers. The environment for the classical computer will be a room temperature standard hardware, whereas in supercomputers, the environment will be large facilities, high energy consumptions, whereas in quantum computing, requires ultra cool environment, error correction. Applications. In classical computers, word processing and browsing data will be taken. Some of them applications in supercomputing, weather forecasting, nuclear stimulations, AI training in supercomputers, whereas in quantum computing, drug discovery, financial modeling, and secure communications. Limitations. Classical computing slower for complex numbers, whereas in supercomputers limitations are expensive, energy intensive, still classical limits. In quantum computing, the limitations are fragile qubits, limited scale, experimental stages. Next, whereas coming to the quantum key distribution, quantum key distribution is a method for securely sharing secret encryption key between two parties by encoding key bit onto individual photons. Next, coming to the how it works. It works on the photo transmission. Allies send signal photons to Bob over a optical fiber or a free space link, each carrying a random quantum state 0 or 1. Quantum measurement. Bob measures these photons and they communicate classically about the basis of their measurement. Key generation. They compare their measurement results to detect, identify matching photons, forming a shared random bit string. U-dropping detection. If an U-dropper tries to interrupt and measure the photons, he intensely disturbs their quantum state due to the non cloning theorem and measurement disturbance principles. Error detection. Alice and Bob compare a subset of their key bits as discrepancy reveals U presence, prompting them to discard the compared key and try again. Next, coming to the benefits of quantum key distribution, physical based security. It is impossible to create identical copy. Security comes from the laws of quantum mechanisms, not mathematical assumptions, making it secure even again future quantum computers. Tampered evidence. Tampered evidence rooted in a fundamental law of quantum mechanisms like Heisenberg uncertainty principle, non-cloning theorem. Long-term security in quantum key distribution is crucial for sharing data. The encryption key generated and shared today will remain secure for decades or even centuries. Next, coming to the real world applications. Drug discovery. Quantum computing accelerates molecular stimulations to design new drugs faster and more accurately. Finance and risk management. Quantum algorithms optimize portfolio and improve risk analysis in complex financial markets, banking, and investment firms using quantum computing. Logistic and supply chain optimization. Quantum computing enhances route planning and resources allocations for global supply chain. Cyber security. Quantum cryptography strengthens secure communication against classical and quantum attacks. AIML, artificial intelligence and machine learning. Quantum algorithms accelerates training of complex AI models. Quantum machine learning boosts pattern recognitions and data processing beyond classical limits. Next, energy and material sciences. Quantum stimulations helps designing better batteries, solar panels, and superconducting. Quantum stimulations enable breakthroughs in battery designs, superconductors, and sustainable energy materials. Telecommunication. Quantum technologies improves ultra precise sensing and next generation communication networks. Quantum sensing technologies improves precise in navigation, medical images, and telenetworks. Telecompanies are experimenting with quantum optimization to enhance network performance. Thank you.